So in section 4.2, every problem has a bit of data, and we're going to use the data to generate equations, and then we're going to make predictions about the future using the equations that we create. And I really didn't like problem 1, so I don't want to do every problem in this section. I'm redoing this video, and I really didn't like this problem 1. It's probably not the best introduction to this, and I'm going to skip number 1. Number 2 is almost a duplicate of number 1, which is kind of equally a bad way to start. I'm going to start this section with number 3, and so when you go to do the homework, you can skip number 1. I'm going to do number 3 for you. I'll do 3, 4, and 6, and I'll let you do number 5. It's a really short section. So in the problem 3, I'm given a table, and it basically says over the years the number of farms have decreased in the United States, but the size of the number of acreage that the farms are, the size of the farm is getting bigger. There's less farms, but they're bigger. In 1910, the average farm was 139 acres, and then they get bigger and bigger. In 1997, the average farm was 487 acres. I'm sure I stole this problem from the internet. I don't really have any more current data. The data is already obsolete, but the nice thing about having obsolete data is that 5 years from now, it's still going to be obsolete, whereas if I use something that had current data, then it's going to start to look obsolete, and we'll just live with this. So each one of the bits of information here is a year, and then how many, the average farm, how big it is. The first thing I'm supposed to do is make a scatterplot, which is just a graph of the data, considering the data as points. And it says let x be the number of years since 1900. I'm going to create points for this function and enter them on my calculator. And the first point I'm going to enter, I'm going to use 10 to represent the year 1910. And I'm going to type in 139 for the average size of a farm in acreage. The second point I'm going to do is the point 20 to represent the year 1920, and then the average farm was 149 acres, and then 30 to represent the year 1930, and then the average farm was 157 acres. So I'm going to enter each one of these as a point on my calculator. In this section, I'm not going to do any graphing by hand. I'm going to use my calculator to do all my graphing. So the first thing I'm going to need to be able to do is enter points on my calculator. To enter points on my calculator, God, these things, it's tough for me to get my calculator to show up. So to enter points on my calculator, the first thing I'm going to do is I'm going to hit my stat button. Once I hit my stat button, it's going to be on edit, which is a place I want it to be. So once I hit my stat button and it says 1:edit, I'm going to hit enter again. I haven't actually hit enter yet. I just hit the stat button. My calculator goes right to where I want it to be, and now I'm going to hit enter. When I hit enter, it's going to pull me to a screen that has a couple lists. My calculator has list 1, list 2, and list 3 that I could see. If I arrow up to the top and kind of move around, I have lots of lists on my calculator, from list 1 to list 6. If you can find list 1 and list 2, you're in a good position. If you can't find list 1 and list 2, you need to use any two lists on your calculator, and you have to note where you put the x's and where you put the y's. I'm going to use list 1 for my x's and list 2 for my y's. My list 1 has numbers in it already, and I'm going to get those numbers out of my list by hitting the delete button. So my calculator, I'm just going to keep hitting delete. Every time I hit delete, it takes one number out of the list. So I hit delete a bunch of times. My list 1 and my list 2 are clear, so hopefully you can find list 1 and list 2. If you can't, just any two lists that you know the name of will be fine. In list 1, I'm going to put the point 10 for 1910, 20 for 1920, 30 for 1930, 40 for 1940, 50 for 1950, 59 for 1959, 69 for 1969, then 78, 87, and 97. So I entered all the values that I'm going to use for x's. I'm going to arrow up and get into list 2. In list 2, next to the 10, I'm going to type 139 for the acreage, then 149, 157, 175, 216, 303. I should make sure I've entered every number right. If I don't enter every number right, I can't get a right answer. So 10, 139, 20, 149, 30, 157, 40, 175, 50, 216, 59, 303, 69, 390, 78, 449, 87, 462, 97, 487. Everything is in fine. Now I have the data in. I'm going to want to graph the data. Part A says make a scatter plot of the data. A scatter plot's just a graph of the data. To get a scatter plot of the data, first you have to enter the data. The next thing I need to do is make my calculator able to do a scatter plot. To do that, I hit the second button and then the y equals key. So after I've entered the data, I hit the second button and the y equals key, and that activates the stat plot. Once I get into the stat plot, probably most of my stat plots say off. I'm going to have the 1 highlighted and I'm going to hit enter. And then my calculator takes me to the stat plot 1. Right now it's off. I need to get my cursor blinking on. And once I get my cursor blinking on, I hit enter. So now the black is on and the off is unlighted or unlit. I'm going to have the upper left hand corner highlighted on the type. So if that's not highlighted, enter to the upper left hand corner and hit enter. And then my x's are in list 1, my y's are in list 2. If my x's were in list 3, I'd hit the second and the 3 and I would change the x's to list 3. So wherever you put the x's needs to be in list 1. My x's were in list 1. To get it there, I would just type second and 1 for list 1. And my y's are in list 2. So this is fine and that marking is fine. So now I have, if I hit my y equals button, the plot 1 is on, which is a beautiful. So it's ready to do a stat plot. I want to clear out any function that's in here. So now I'm ready to graph. To do my stat plot, I'm going to hit the zoom button and then go down to number 9 that says stat. So it's zoom. I'm going to arrow down to number 9 and hit enter. And when I do this, zoom stat, the calculator will set the window to fit the data. So now I'm going to hit enter and it graphs the data for me. And that data surprises me, but it kind of is what it is. That's the end of part A. Make a scatter plot of the data. I'm not going to do any graphing. I don't want to see any graphing in your homework. Just say, see your calculator to graph the data. The next thing I need to do is use my graphing calculator to find an equation to fit the data. And this is called linear regression. Finding an equation of a line, finding a linear function to fit the data, you have to do linear regression. So to do part B of number 3, I'm going to come up with an equation of a line that fits the data, the best equation of a line that can fit that data. This data isn't particularly linear, but I'm going to find an equation of a line that fits the data. To do this, to answer part B of number 3, I'm going to hit the stat button. And after I hit the stat button, I'm going to arrow over to calc. So I used my right arrow and arrowed over to calc. And then I'm going to go down to number 4. I'm going to arrow down to lin regression AX plus B. And then I'm going to hit enter. When I hit enter, my calculator is gonna get away from this screen and go onto the main screen. So when I hit enter now, I hit my stat button, I arrowed over to calc, I arrowed down a few times to linear regression. That's up to here. Now I'm going to hit enter. My calculator says linear regression ax plus b. It's going to find an equation of a line, and it doesn't use m for slope, it uses a for slope. I'm not sure why that's the case. On my main screen after this, my calculator needs to say L1, L2, comma Y1. What it's going to do is it wants to know where you put your x values. I put my x values in list 1. It wants to know where I put my y values. I put my y values in list 2. And it wants me to know where it wants me to put that equation in terms of graphing that equation. I'm going to put it in y1. So to get my calculator to have an L1 next to the list 1, I'm going to hit the second button and then the 1 key. When I hit second and then 1, it's going to put a list 1 next to the linear regression. Then I'm going to type my comma. I'm going to hit the second button and a 2 to get the list 2. Then I'm going to hit my comma, so it has x's are in list 1, y's are in list 2. Now I need to tell it where I want it to graph it, and this is the tricky part. To get it to say y1, you have to hit the vars button. So I'm going to hit this vars button right next to the clear key. Arrow over to y-vars. So I hit the vars button. I arrow over to y-vars. I hit enter on function. So my calculator naturally takes me to function. I'm going to hit enter for the first time. So I hit vars, y-vars, hit enter on function, and then I'm going to hit enter on y1. My calculator pulls me right to that y1. And once my calculator has that y1 displayed, I'm going to hit enter. And when I hit enter now, it puts the y1 next to list 1 and list 2. So what my calculator is going to do, it's going to come up with an equation of a line that fits the data the best an equation of a line can fit the data. It's going to tell me what the equation is after I hit enter, and it's going to graph that equation for me. So I'm going to hit enter one more time. My calculator comes out with some junk. It says the equation of this line is in the form y equals ax plus b, where a is 4.717948718, and b is 37.93076923, and then it says what r squared and r are. Your calculator might not have these yet, and let me get your calculator to put those there. So if your calculator didn't display these, I'll get your calculator in the mode to display these. The r is the important one of these numbers. If the r is bigger than 0.8, the line is considered a decent estimator. So the line is a good predictor of the data if the r that comes up is bigger than 0.8. If your calculator didn't come back with an r or an r squared, to get your calculator to get an r squared, you have to do this. You hit the second button. So if your calculator gave an r, you're okay. To make the r appear, if it doesn't, follow this. Hit the second button and then the 0. And on the 0 is the catalog key. So I hit second and 0. And it brings me to a long, long list. I have to enter arrow down in this list for a long, 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 long time. Eventually, I'll get to diagnostics on. There it is. Right now, if you didn't get an R, your diagnostics off is on. You're just going to hit the arrow over to the diagnostic on, and hit enter twice. I'll go enter and enter. And now if you redo the computation, go stat, calc, down to linear regression, second and 1 for L1, comma, second and 2 for L2, comma, vars, y-vars, enter on function, enter on y1, And when you hit enter, it will give you the R's. So if you didn't get the R's, you have to turn your diagnostics on by hitting second and 0, going all the way down to diagnostics on. And once you get to diagnostics on, you just hit enter twice, and then you're done. So now my calculator, what it's done, it's given me an equation of the line that's a good predictor to fit the data. When I go to write an answer, part B says use a graphing calculator to fit a linear function to the data, and my equation is going to be y equals to... Alright, so I just got a phone call, so now I've kind of lost my train of thought here. Anyways, I think I was coming up with an equation of a line to fit the data. It doesn't say anything about rounding. I don't want to carry a bunch of decimals. Let me carry 2 decimals. And the equation of the line I'm supposed to create is going to have the a in front of the x. And for the a, I'm going to round that to 4.72. That 4.717, I'm going to write to 4.72. So I'm going to write y equals to... and then 4.72 next to the x, and then after the x is the b, that's the b that we're used to calling b. I'm going to round that to 2 decimals, and I'm going to write it as 37.93 because the 0 makes it so I don't have to round up. Now this would be an adequate answer to part B, but it's not in function notation. And it might be nice if I change the y to a function symbol because I'm asked to find a linear function, and maybe change the x to something like a t for time. So I'm going to write or, and right next to this I'm going to write an answer. And I'm going to use function notation. I'm going to write a for acreage, t for time, and then I'm going to change that x to a t. I'm going to say a of t equals 4.72 times t plus 37.93. Those both would be good answers for part B. I kind of like the second answer better, but if this was a test question, I'd live with either. So I made a scatter plot of the data. I used my graphing calculator to fit a function to the data, and I know that the data is a good fit because anytime the R is 0.8 or bigger, then the line is a good predictor of the data. An R of 1 would be perfect predictor. So this is since the R is bigger than or equal to 0.80, it's a good fit. If the R was less than 0.8, then I probably wouldn't use that equation to make predictions. I'd come up with a different kind of regression equation to make a prediction. Part D, it says graph the function with the data. And for this, I'm going to say see my calculator again. And the beautiful thing is, if I just hit my graph button right now, my calculator is going to graph that line for me because I told it to do it. If I look at my y equals, it put the equation in my y equals. When I did the linear regression, the y1 part of my linear regression took the equation and put it in y1. So done with that part. I'm just going to say see my calculator. Now for part B, predict the average acreage in 2010, I need to use my equation and put something to represent 2010. If I put 10 to represent 1910, I can't put in 2010 for the year 2010. The number that I'm going to plug into the equation to predict the average acreage for 2010 isn't 2010. To figure out what number to put in, I put 97 for 1997. I would have plugged 2000 for the year, for 100 for the year 2000. To figure out the year, the number to put in for the year 2010, I take the year minus the base year. Since I'm using year 0 for 1900, year 10 for 1910, 20 for 1920, if I do this subtraction, if I put 110 in for the year, that will represent the year 2010. Since 0 is 1900, 10 is 1910, 110 is going to be the 2010. To predict the average size of a farm in the year 2010, I'm going to plug 110 in for the data and go 4.72 times 110 plus 37.93. I didn't put anything about rounding here, so I'm going to have to round on the cuff. So I'm going to do 4.72 times 110 plus 37.93. And that tells me the average farm in the year 2010 is 557.13 acres. I'm just going to leave it rounded like that. All of these numbers didn't have any decimals. If I just said 557 acres, that would be fine. When I go to answer part E of number 3, I'm just going to say the average farm. Don't have much room here, so I'll say it's 557.13 acres. All right, I'm not sure that that's good enough for you to go and be independent of me. But if you want to, the only homework problem you have to do for this section is problem 5. You might be able to do problem 5 by yourself. So pause the video if you can get it done. Don't watch any more of the video. If you can't, watch me do problem 4, and maybe that will get you as far as you need to go. So in problem 4, it says the winning times for the women's 400-meter freestyle swimming event in the Olympics from 1936 to 1996 are given by this table. So in 1936, the time in the 400-meter was 5.44 minutes, because the time is in minutes. 1996, it's 4.12 minutes. So the times are getting progressively shorter, although they're kind of flattening out here. So part A says make a scatter plot of the data. Let X represent the number of years since 1900. So for this first point, instead of writing 1936, the time was 5.44 minutes, I'm going to say 36, 5.44. 36 is going to be 1936. The second point I'm going to enter 48 for the year 1948, and the time is 5.30 minutes. I'm going to enter, there's 4, 8, 11, 14 points on my calculator to get this problem started. And then I'm going to make a scatter plot. Real quickly, let me go to my y equals and clear out the function that's in there. Now I'm going to hit my stat button, and I'm going to enter the data. I'm going to hit enter on stat, and I'm going to delete every single number in list 1 by just continually hitting the delete key. Every time I hit the delete key, it gets rid of a number in a list. If you want to, you can delete an entire list all at once by using the clear button. If I hit the delete button when my list 1 is there, it's going to delete list 1. It's going to create a mess for me. If I hit the clear button when I have the list 1 highlighted, followed by enter, it clears the whole list. So I need to get the list entered cleared. Now I'm going to enter 36, 48, 52, 56, 60, 64, 60, 64, 68, 72, 76, 80, 84, 88, 92, and 96 for my data points. Go over to list 2 and enter the y's. 5.44 minutes, 5.30 minutes, 5.20, 4.91, 4.84, 4.72, 4.53, 4.32, 4.16, 4.15, 4.12, 4.06, 4.12, 4.12. Make sure I have all the data in right, because if you have the data in incorrectly, then you can't get a good answer. So I'm just checking each point one at a time to make sure it matches the points that I have, listed here. Down to 72. I'm just physically just checking to make sure I didn't do something stupid. Good enough. Have the data in perfectly. Once you have the data in, to make a scatter plot, you hit the zoom button, go down to option 9, and hit enter. So I hit zoom and then 9, I'm going to hit enter. It's going to plot the data. You see the data starts off linear, then it kind of flattens out. This flattening out part is going to make my predictions maybe not so wonderful, but it is what it is. we're not going to do graphs by hand. So for the scatter plot, I'm just going to say, see my calculator. Next thing in part B, I'm going to use my calculator to find a function to fit the data. To do this, you hit the Stat button. You arrow over to Calc. You arrow down to Linear Regression. After you get to Linear Regression, you hit Enter. And then after Linear Regression, I need List 1, List 2, Y1. I hit second and 1 for List 1, and then the comma. And then second and 2 for List 2, then the comma. Then vars, arrow over to yvars, hit enter on function, hit enter on y1. There's my linear regression, list 1, list 2, y1. When I hit enter, it's going to give me the equation of the line, and I'm going to round to 2 decimals. So my equation is going to be y equals negative 0.0, it says 26, I'm going to round that to 0.03 for a, and then I'm going to put the x in. And then plus, I'm going to round that to 6.42. The 1 in the second decimal for the B has a 7 after it, so I'm going to round that to 6.42. And it gives me the R as negative 0.958. The R is negative because the slope of the line is negative. So if the absolute value of this is bigger than 0.8, it's a good fit. So this is an answer for part B, but it's not in function notation. If you want to clean this up and put it in function notation, I don't know, it might be W for the winning time in the Olympics. I might do W for winning, T for time, equals negative 0.03T plus 6.42. That seems reasonable. And since the R is negative 0.96 rounded, it's a good fit. As long as the absolute value is bigger than 0.8, it's a good fit. And the absolute value of negative 0.96 is positive 0.96. Now I'm going to graph to do part D, and I'm going to say, see my calculator. So I'm going to hit my graph button, and it graphs it for me. And you'll see my graph keeps going down while the data starts flattening out. I'm worried that when I go to make a prediction in the future, that it's going to predict a time that's off the screen where the times are really flattening out. So when I go to use my equation, even though it's a good fit, I'm worried that the prediction might not be that accurate, specifically because at first, at the beginning, the points were going down at a constant amount, and then the time started flattening out. The line doesn't take into consideration this flattening out, and when I make a prediction using the line, it might predict a time that's too aggressive, not really close to reality. But for what it's worth, I'm done with part D. I've done my graph. I'm going to say, see my calculator. Now I need to predict the winning time in 2020. I need to plug a number in for T that represents 2020. Because time 0 is 1900, the time that I'm going to plug in to estimate the winning time in the year 2020 is going to be 120, because 2020 is 120 years after 1900. To estimate the winning time in the year 2020, I'm going to plug 120 in for the time. And whatever it gives me to, that's going to be the time in minutes. And I can't do that in my head. I wish I really care that I can't. So now to do this on my calculator, back to the main screen, negative 0.03 times 120 plus 6.42, and I get 2.82 minutes as the estimation of the winning time. Quite honestly, that's a really aggressive estimation. But when you're using regression to fit data, it can give you answers that are bang on, or it can give you answers that don't make sense, because the data, you can see, it doesn't really fit the line so well at this part of the data, so maybe it's not the best predictor, but that's the best I can do with the information I'm given. So we have problems 5 and 6 left. Let me just do problem 5, which will be your only homework. So when you go to turn in your homework for this section, if you turn your homework in, You don't have to do number 1. 3 I did, and 5 I'll do. So in problem 5, it gives me the average salary, S, in millions of dollars for professional baseball players between 1996 and 2002. They're all shown in this table. I'm supposed to make a scatter plot of the data, and it says use XB, let X be the number of years since 1990. So 1996 is 6 years after 1990. The first point I'm going to enter is 6 for the year 1996 and 1.1 for a salary of $1.1 million. The second point, when I go to do my scatter point, I'm going to use the number 7 to represent 1997 and 1.3 million for the salaries. So the numbers I'm going to put in my X column are 6, 7, 8, 9, 10 for 2000, 11 for 2001, and 12 for 2002. Make those 6, 7, 8, 9, 10, 11, and 12 my X's. I'll leave my Y's the Y's. The X's represent the years, where 7's 1997, 8's 1998, and the salaries are in millions of dollars. So it means 1.1 million, 1.3 million, up to 2.3 million. Let me make a scatter plot of the data. Easy enough to do. To make a scatter plot of the data, first I have to enter the data. I hit my stat button. I hit enter, and I'm going to delete everything in list 1 by just repetitively hitting the delete button when I'm on the list. Go over to list 2. I can clear it by just going up to the top of the list and hitting clear and enter. However you clear the list, it doesn't matter. You just need to get the lists clear. I made my X column, and now I'm going to do my Y column. Make sure I have all the numbers in right. If you have one number in wrong, you'll get the answer wrong. So 6, 1.1, 7, 1.3, 8, 1.4, 9, 1.6, 10, 1.8, 11, boom. Looks like the data's in right. So now if I just hit zoom and go down to option 9, it'll draw a stat plot. And that data looks very linear. It doesn't flatten out like the last data is. So this is a very linear data set. So for part A, to make my scatter plot, I'm going to say C calculator. And for part B, I'm going to find the equation of the line that fits the data. To do that, I hit my stat button. I arrow over to calc. I arrow down to linear regression. I hit enter. And then I do second and 1 for list 1, comma, second and 2 for list 2, comma, vars, y vars, enter, and enter for the y2, 1, and hit enter. And now it tells me the equation is y equals to 0.2 for the A times x minus, I'm going to round that to 0.14. That's an equation not written in function notation. The R is 0.99, so it's an amazingly good fit. When I get down to the next part, since the R is 0.9, which is bigger than 0.8, it's a good fit. If I wrote this as an answer for part B, that would be fine. But it might be better if I did this. Maybe write S for salary, T for time, and wrote salary with respect to time is 0.2 times T minus 0.14. Both of these would be good answers for part B. This would be the better answer because it's using function notation. The line's a good fit when I go to do part C, because the R equals 0.99, and that's greater than 0.8. For the graphing part, I'm not going to do this graph by hand. I'm just going to say see my calculator. And when I go to see my calculator, I'm just going to hit the graph button, and it's going to graph the line for me because it's already stored in the y equals. So the graph is done. Last thing I need to do is predict the average salary in 2018. To figure out the number to plug in for X, I'm going to take 2018 minus 1990. So 2018 minus 1990 is going to tell me the number to plug in for X. I'm going to plug in 28 for X, or T, to get the average salary in 2018. So to use my formula to predict the average salary, I need to know what number to plug in for the year, and 28 is going to represent the year 2018. I'm going to find S of 28 by going 0.2 times 28 minus 0.14. On my main screen, I'll go 2 times 28 times minus 0.14. And that gives me the average salary is $55.86 million. My gosh, $55 million. I don't think that's right. Oh, it's 0.2. Oh, it's going to be 0.2 times 28 minus 0.14. And 5.46 million feels so much better than a $55 million salary. So the average salary in 2018, according to this prediction, is about 5.46 million. The instructions said round to the nearest tenth, which is round to one decimal. I'm going to round that up to 5.5 million. And for my answer, I'm going to say 5.5 million for my average salary. If I wanted to write a sentence, I could say the average salary in 2018 should be about $5.5 million. So I won't do number 6, I won't show you number 6, and that will be the end of this section. So we only had a few problems. It's a really short section, so hopefully it feels okay.